Okay, so let's solve this analytic trigonometry equation. 3 cosine of theta plus 3 equals 2 sine squared of theta, where x is on the interval from 0 to 2 pi. Okay, so a quick reminder. We know from our analytic trigonometry that if I have an angle theta with a unit circle and have the hypotenuse of this triangle of 1, then this side is sine of theta and this side is cosine of theta. Using the Pythagorean theorem, I know that sine squared of theta plus cosine squared of theta is equal to 1. Manipulating this equation, I have that the sine squared of theta is equal to 1 minus the cosine squared of theta. Or I have that the cosine squared of theta is equal to 1 minus the sine squared of theta. Okay. These are generally referred to as the Pythagorean identities. Okay. So those are generally referred to as the Pythagorean identities. Okay. So let's go ahead and rewrite our equation that we're trying to solve. We're trying to solve 3 cosine of theta plus 3 is equal to 2 sine squared of theta. All right. So the first thing I notice is that this cosine and this sine squared aren't the same function. However, I should also notice that if I replace sine squared with 1 minus cosine squared, then this entire equation can be in terms of a single trigonometric function, the cosine. Right? So I can replace this and have 3 cosine of theta plus 3 is equal to 2 times 1 minus cosine squared of theta. So once again, all I did was replace the sine squared of theta using a Pythagorean identity. Okay. Then hippity hoppity, my distributive property, and I have 3 cosine of theta plus 3 is equal to 2 minus 2 cosine squared of theta. If I rearrange, right, move everything to one side of my equation, I'm going to have 2 cosine squared of theta plus 3 cosine of theta plus 1 equaling 0. So now I have this quadratic form of an equation in terms of my function cosine. My next step is to do what's known as a u substitution, and we're going to let u equal the cosine of theta. All right, so I'm going to make the substitution that u is the cosine of theta. So that's going to give me 2 times u squared plus 3 times u plus 1 equaling 0. So now I'm at a step closer to being able to solve this equation, since now I've converted it to a quadratic equation in the variable u. Okay. So I could factor this if possible. We'll see. I could factor this if possible. Right? And of course, if I don't know how to factor, I could always use the quadratic formula, right? So u is equal to opposite b plus or minus the square root b squared minus 4ac all over 2a. All right, so I could use that quadratic formula if I wasn't quite as familiar. But over here, this is a 2u squared is a prime number, so I can have 2u and then not 2u again because that would give me 4. So 2u and u. Right? And then I need a product of 1, so plus 1 and plus 1, and verify that that works. So 2u times u is 2u squared, 2u times 1, 1 times u, that's going to give me 3u, and then 1 times 1 is going to give me u. So if I solve this is going to mean that u needs to be equal to negative 1/2, or u needs to be equal to negative 1. But remember, what did we substitute for u? We said u was cosine of theta. So now I need to go back and solve for my original variable. So I'm going to go ahead and go back and solve for my theta. So I can say the cosine of theta equals negative 1/2, right? Or the cosine of theta equals negative 1. Okay. Now for this particular problem, for the cosine of theta is negative 1/2, I know that the cosine is negative in the second quadrant and in the third quadrant. And I know I have a reference angle. And with the ratio of 1/2, I know that the reference angle in radians is pi over 3. For negative 1, if I'm working with negative 1, I know that cosine of theta is negative 1 when I go to pi radians. So what does that tell me? That tells me the following. That tells me that theta has to be equal to an angle in the second quadrant here, which would be 2 pi over 3, right? Or theta has to equal an angle in the third quadrant, which would be 4 pi over 3. But for this one, theta would need to equal pi. So it seems like I have 3 solutions. I can check to see if that's as many solutions as I would have. If I were to happen to graph, right? If I were to happen to graph my particular graph, I can look over here and I can see, hey, I've got 3 cosine of theta up in the blue. I've got 2 sine squared of theta in the red, right? So 3 cosine of theta plus 3, my original function, right? I've got those original functions. 3 cosine of theta plus 3, 2 sine squared of theta. And it does appear that they intersect 3 times. And those 3 intersections, right, are 2 pi over 3, 4 pi over 3, and pi. Of course, if I wanted to, I can go second, right, and calculate the intersection, right? So second, calculate the intersection between my 2 graphs, right? And I can arrow near the point of intersection, press enter once, twice, thrice, and it tells me the intersection is about x is 2.0943. And if I'm not sure what that value is, there's 2 pi divided by 3, 2.0943. Right? So I've got my various solutions, and on the interval, there are only those 3 solutions. Okay? So this is a first of several examples on solving equations in analytic trigonometry.